Hi everyone. Today we're going to talk about orbital notation. Now the first thing I want to talk about is review some of the things that we've already covered. First of all, the subgroups S, P, D, and F. Now, if you remember looking at our S block, our S subgroup, there are two places where electrons can be occupied. This is one orbital that holds two electrons. For our P block, we have 6 places where electrons can be held and 3 orbitals. Remember, there are 3 dimensions, the X, Y, and Z for the barbell, for the figure 8 shape. So we have 1, 2, 3, 4, 5, 6. 3 orbitals that will occupy those spaces. For the D block, we have 10 spaces. So that means there will be 5 orbitals that holds 10 electrons. And for the F block, we have 14 spaces. That will be 7 orbitals that hold 14 electrons. So every orbital can hold up to 2 electrons. And what we use for orbital notation, we use to show the unique spin of every electron in an atom. Now the way we use this is we denote arrows. Okay, every orbital will have 2 electrons, like I just said. F block has 14 spaces, 7 orbitals, so each orbital holds 2. Okay, they will spin in 2 different directions, and we refer to this as an upspin and a downspin. Now the reason for this is that when 2 electrons occupy the same orbital, electrons are negatively charged, so they repel. So they're going to push away from each other and they spin in these opposite directions. Okay? So we have a special kind of electron configuration that we use to denote these upspins and downspins. Okay? So again, look, the S subgroup has 1 orbital. The P subgroup has 3 orbitals, so it can hold, S can hold 2 electrons, P can hold 6 electrons, 6 spaces across. The D subgroup has 5 orbitals, and the F subgroup has 7 orbitals. The D can hold 10 electrons, and the F can hold 14 electrons. Okay. Now, to put this into a little bit of perspective and where we use this, let's again review a couple of things with sulfur. Okay. Sulfur has a atomic number of 16, and it is in this 16th family, the 16th group. So let's look first at the Lewis dot. So that means it has 6 valence electrons. So 1, 2, 3, 4, 5, 6. Next unit, our valence electrons are going to be very, very important to what we use for bonding. Okay. Next, let's look at the electron configuration. So sulfur has always start at 1. So 1s, 2, 2s, 2. So 1s, 2, 2s, 2. We keep going. 2p, 1, 2, 3, 4, 5, 6. 2p, 6. 3s, 2. 3s, 2, and the next 3p, 1, 2, 3, 4. So 3p, 4. All right. So this is the electron configuration of sulfur. And to check yourself, you can add up your exponents. 2 plus 2 plus 6 plus 2 plus 4 is going to give you a total of 16. So you can always look back and make sure that your numbers, your exponents are adding up correctly. Okay. Now let's use this information to talk about our orbital notation. So the first thing, we have an S subgroup. So we're going to draw an orbital box. So S has one orbital. Okay. S has one orbital, remember? S has one orbital. Okay. The P block has 3 orbitals. S has one orbital and P has 3 orbitals. Okay, so we can go back through and fill in our electron configuration underneath the correct orbitals. So we have 1s2, 2s2, 2p6, 3p2, 3p4. I'm sorry, 3s2, my mistake. 3s2, 3p4. Okay, now what we're going to do is we're going to fill in our arrows depicting our upspin and downspin. Okay, now the reason that we talk about them spinning in opposite directions, this is directly correlated to the Pauli exclusion principle. The Pauli exclusion principle states that no two electrons can spin the same way in the same orbital. Okay, and that's because of their electric charge. They're going to repel against each other. All right, so what we're going to do is we're going to fill in our arrows. So 1s2, there are 2 electrons, and we have to show both electrons with an upspin and a downspin. Now that is filled. 2s2, upspin and a downspin. 2p6, we have an upspin, and then we go back and we fill in our downspins. Now that becomes more important on the 3p. I'll show you why here in a second. 3s2, upspin and downspin. 3p4, so we have 4 electrons. We have 3 upspins and 1 downspin. Now, how come I did not do this? Upspin and a downspin, upspin and a downspin. Because this is not correct. This correlates directly to something called Hund's rule. Hund's rule states that orbitals, sorry, my pad is, orbitals must be filled upspin first before downspin. And it all has to do with being in a single atom. You've got 3 orbitals there, and you're not going to lopside the atom by having electrons hanging out in one orbital. They're going to put one atom in one electron in one orbital, a second electron in a second orbital, a third electron in a third orbital, and then you go back and start pairing up. So we denote that with our upspins first. So the first orbital, upspin, second orbital, upspin, third orbital, upspin. Then we can go back and pair. When we're talking about a filled subgroup, everything, each box is going to be filled. But when we have a situation where it's not filled, you have to make sure you fill in your upspins first, okay? Let's see, let's do one more example here. Let's look at Let's look at silicon. Silicon is a 14, and it starts with a 1s2 and a 2s2 and a 2p6 and a 3s2 and a 3p2. All right, so S group has one orbital, S group has one orbital, P group has three orbitals, S group has one orbital, P group has three orbitals. All right, and now we're going to go through and we're going to put our up spins and our down spins. 2 electrons, 2 arrows. 2 electrons, 2 arrows. 6 electrons, 6 arrows. Okay, 2 electrons, 2 arrows. And our P group, 2 electrons, but remember we must fill the up spins first before we go back and put in down spin. So it would be 2 up arrows. Okay, and that's orbital notation. So now that we've learned this really long procedure, let's talk about a shortcut. And this is noble gas configuration. Noble gas configuration is, like I said, like a shortcut. Sometimes periodic tables provide the noble gas configuration because it can be written in a much shorter format. Okay, so again, let's look at sulfur. So sulfur, just the electron configuration: 1s2, 2s2, 2p6, 3s2, 3p4. In electron configuration, what we're going to do is, in noble gas configuration, we're going to use the electron configuration and show a portion of the configuration. So the first thing we do is we go to sulfur and we figure out which noble gas precedes the element. So in this case, neon precedes sulfur. So let's look at neon's electron configuration. Neon is a 10, so it is 1s2, 2s2, 2p6. All right, now for noble gas configurations, what we're going to do is we're going to draw some brackets. So I have sulfur here, and I'm going to put in brackets neon. And when I do that, this is the same as writing that whole configuration. So we don't have to write that section. Then all we do is continue on with everything past neon leading up to sulfur. And for the beginning elements, it's not that big of a shortcut. But when we look at something, say, like uranium, which is a 92, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 5s2, 4d10, 5p6, 6s2. Remember, after 6s, we come down here to the lanthanides. So after 6s2, we have 4f14. And then we go back into the D's, so that would be 5d10. And then we'll finish that row after 5d10 with 6p6. And then we go to 7s2. And after 7s2, then we get to the actinide. So then we have uranium, which is 5f4. Not 14, 4. And that's the full electron configuration of uranium. Now, let's look at the noble gas configuration. We find out which noble gas precedes uranium. The noble gas that precedes uranium is radon, number 86. So, after radon, we only have to write 7s2, and 5f4. And that's a huge shortcut to be able to cut all of that extra off at the beginning. Okay, so like I said, the beginning ones, it doesn't seem like that big of a shortcut, but when you get into the really long electron configurations, it's a very, very huge shortcut. Okay, and that's about everything. Okay, next unit we're going to be discussing bonding and how molecules are formed. So until then, work together, help each other, make the world a better place. See ya.